Hi friends, in this session we will see about the stresses and deflection in solid and hollow circular shafts. So how the stresses are produced and how the deflections are happening in this circular shafts. So before getting into this, we have to recollect some of the things. So first you should know that the torsional equation. So in the previous session, just we have derived this equation. This equation is T by J equal to tau by R equal to G theta by L. And some of the assumptions we were made, and also to derive this equation, some of the components we have seen them. Just we have derived the shear stress and shear strain and as the torque, and everything just we were simplified, and finally we got the torsional equation, and also just we saw some of the summary also. So now in this topic we will see about what is the importance of knowing the stress and deflection in the solid and hollow circular shaft, and what are the real world applications where this is used, and what is the shear stress distribution, so how it is happening. Okay, so here in this unit it is given as solid and circular shaft. How this shear stress distribution is produced, how we can calculate this, and also some of the design considerations we were made. So everything we will discuss in this topic. So what is the importance? So here if you are taking this to maintain the structural safety, so here this is very important. So the designing of any component is very easy, but we have to check that whether it is properly running, and also the lifetime of that structure is okay or not. So everything we have to it should be measurable. So that is the structural safety, and also the serviceability. There is a lifetime of that the element. It is very important, and also the efficiency. So here if you are taking that, if you are constructing any building where the places where earthquake is there, that is an earthquake prone area. So here that usage of the building, the before the earthquake and the after the earthquake, it should be same. So that is the efficiency of the building should be properly maintained, and also if designing of any structural element, this concept is important, and also to predict the performance of the structural element is also this stress and deflection is very important. So here you can see this. So these are some of the real world scenario. So mostly for analyzing, for doing the analysis of any structural element, we are using the finite element method. That is a FEA. This is our FEM. So for doing the finite element analysis, this the concept of shear stress and also the deflection is a very basic things. So whenever if you are doing the structural analysis, either by means of the software or by the manual, the concept is very important. And how this shear distribution is happening? If you are taking this this is a hollow circular shaft. This is taken here you can see this shear distribution is varying in a triangular manner, which means the shear stress is 0 at the center. So whenever if you are going to the outer diameter, the shear stress is the maximum. So therefore this shear stress is varying linearly. That is a 0 to the maximum. That is center to the 0 at center, and the maximum at the outermost dia. That is a circumference. And the next one, we will see that how this the shear distribution, which is the formula for calculating the shear distribution for the solid circular shaft. So here the stress is nothing but force by area. So here the force is nothing but the torque. So therefore calculating the shear stress distribution for the solid circular shaft, the formula is T into R divided by G. So the T is nothing but the applied torque, and R is nothing but the radius. Okay, and the J is nothing but the polar moment of inertia. So whenever if you are taking this, if it is a circular, the polar moment of inertia is given by the formula pi r power 4 divided by 2. And here whenever if you are taking the radius, it will be varying from 0 to the maximum radius r. Okay. So the formula is for a solid shaft is tau equal to TR divided by G. So now we will see in the hollow circular shaft. So if you are calculating the hollow circular shaft, here if you are taking this, the shear stress will not be never 0 inside the hollow, okay, but it will be less, okay. So the inside it will be less, and it will be maximum at the outermost surface. But as like as in the solid shaft, this shear stress will not be 0 at the center, okay. So it will be some minimum value. So the formula for calculating this shear stress is same, that is a TR divided by J. The thing is the calculation of polar moment of inertia, that is a J, can be represented by pi into capital R power 4 minus small r power 4 divided by 2. So this is the outer radius and this is the inner radius. Okay. And next, if you are going for the maximum shear stress. So here the maximum shear stress for a solid shaft is given by TR divided by G. So or it can be represented by 16 T divided by pi d cube. That is the if you are substituting the polar moment of inertia J, you can get this derivation. And similarly for the hollow shaft, this is 16 T divided by pi d power 4 minus capital D power 4 minus small d power 4 divided by D. So where the capital D is the outer diameter and the small d is the inner diameter. Okay. And the next one is the angle of twist. The angle of twist for solid and also the hollow shaft is given by theta equal to TL divided by G into J. So where T is the torque and the L is the length of the shaft and G is the rigidity modulus and J is the polar moment of inertia. Okay. So here whenever if you are substituting the polar moment of inertia for a solid is different and the hollow shaft is different. If you are substituting, you will get the angle of twist, that is a theta. So here the important thing is the design conservation. Okay. So here for hollow shaft, the preferred thing is a weight saving is very important. Okay. So the weight savings and also it should be the stronger and stiffer than the solid shaft. So therefore nowadays whenever we are going for the steel structure, so we were used in previous years, just we have used the L section. Nowadays we are using the hollow circular section, so which is giving more strength, more stronger than the solid sections, and also the both the strength and stiffness is govern the design of the shaft. Okay. So now if you are summarizing this formulas, what we have seen are the one is the polar moment of inertia. So for a solid shaft is given by pi r power 4 by 2. So similarly for a hollow shaft is pi capital R power 4 minus small r power 4 divided by 2. The r is the outer radius and the small r is the inner radius. So if you are taking the shear stress will be 0 at center but maximum at the outer surface. But here it will not be 0 at center, it will be somewhat minimum, but it is a maximum at the outer surface. And the maximum shear stress is given by the formula 16 divided by pi d cube. And the hollow shaft, it is 16 T divided by pi d power 4 minus small d power 4 divided by D. And the angle of twist is given by TL divided by G into J. And here also the angle of twist is given by the same formula. So now I think in this session you have understood what are the things are involved, what are the terminologies where we were using, and how this derivation is made for a solid section and also the hollow circular sections, and what are the practical applications in the civil engineering field. So whenever if you are designing any structure, these parameters are very important. So it may be by using the software, or it may be a manual calculation, the understanding of this concept is very important. So thank you for listening this video. Thank you.